This is week 7, lecture 3, and we're talking about equilibrium. So this is coming from chapter 9-5 and 9-6, and it'll be equilibrium, equilibrium examples, and then a non-equilibrium example. So equilibrium, when we have a situation of potential rotation. So before, when we were dealing with equilibrium, it was just that the net external force was 0. And that was that there was no acceleration happening. But when we have the potential for rotation, in order for a system to actually be in equilibrium, it needs to have no net external forces and no net external torques, which also means no angular acceleration. So here is our first example of this equilibrium condition. A uniform beam of length L, whose mass is 1.8 kilograms, rests with its ends on 2 digital scales. A block whose mass, capital M, is 2.7 kilograms rests on the beam, its center 1/4 of the way from the beam's left end. What do the scales read? And we're gonna go through this problem, but I mean, first they gave us a nice diagram. The textbook talks about kind of labeling your system boundaries. So the system is the beam itself, not really the scales. The scales just apply a force to the beam. And the other thing that we do with torque is we draw extended free body diagrams. So that means before, it was just like a point and all the forces are acting from that point. With torque, since the distance from the pivot point matters, we need to draw out the object and indicate where the forces act. So let's work on this problem. Okay, so we have our long thin beam, our mass, and our scales. And now let's draw our extended free body diagram. I think I'll just draw it below here. So the forces acting, we're going to have forces up from each scale, kind of contact or kind of like a normal force. And we'll call those FL for the left side scale and FR for the right side scale. And then we will have the weight of the beam going down at the center of mass, which we will say is just the center here. So that's the weight. And then we also have the force from the mass resting on the beam. And so that's going to point down also, and we'll just call that F big M. And for completeness, we can also just draw a quick free body diagram of the mass, and we have its weight force. And then we have the force up from the beam. So that is just, let's see, force on the mass from the beam. And it's not accelerating, 0. So we can say we have this force minus the weight equals 0. So that means that the mass or the force from the mass is just the weight. And this F big M little m is also what I'm calling F big M. And so we can just say that as the weight. So just for completeness on the force there. So then we have our, well, actually, let's define some distances. So I'm going to say, and this is something that happens when you have a system in equilibrium, is you can decide where the pivot is. You can just say, this seems like a place that could rotate. And also one thing to do, it doesn't really apply to this situation, but in other situations, sometimes you can say that the pivot point will be where a bunch of forces are acting, and then you don't have to calculate that force. So anyway, this is our pivot. So we need to know the distances from that to where the different forces act. So this one is obviously the length. This one is L over 2. And then this other one is L over 4. Oops, it's a 4. Okay, and we can just quickly do the sum of forces. The sum of forces is all in the y direction and equals 0 because this is equilibrium. So the forces pointing up are the left and right scale forces. And then pointing down is the force from the mass and the weight of the beam. And we can just leave it at that for now. Then I want to teach you a way to do net force. And I think you should do it this way because it can get confusing, but it's actually not that different than what we've been doing with forces. There's just like an extra couple things to think about. So I make a table of the forces acting. So one column is the force, one column is the distance to the pivot point. Another is either the angle or sine of the angle. And the final column is the sine of the torque. And we'll get to how you figure that part out. So our first force is FL, the left side force. But it's acting at our pivot point, so actually it doesn't apply force. Then we'll just go across the beam, and then so we have the force from the mass, and that one acts at L over 2, or sorry, L over 4. And the angle between the rod, or like the radial line, and the force is 90 degrees, so sine 90 is 1. And we'll get to the sine of the force in a second after we just do this for all of them. The weight force, that one's at L over 2, also sine 90. And finally, FR is at L and also 90. Okay, so how you figure out the sine of the torque is from the direction of the rotation that it would cause. So how we do that is you pinch your, like writing utensil or whatever you have at the point where the pivot is. So I'm pinching it at where force on the left side acts, and then you just pull or push where the other forces are acting. So we'll just go in order. FM is pulling down, so is the weight, and those are both going to make it rotate clockwise, which is negative. So these are negative, and then R is up, and that's counterclockwise, so that's positive. So, and I'll just write our torque equations for each of these. L over 4 times the force equals L over 2 times the weight. And finally, I'll just call this right. L times FR. Okay, cool. Now we do the same kind of sum of forces thing, but sum of torque. So sum of torque, this is equal to 0 because again, we're in an equilibrium situation. I should have included my signs in this. Actually, no, let's not. Sorry, ignore that because we're going to stick to what we've been doing by taking the signs into account when we put it in the equation, just like we do with forces. So I don't want to confuse it. Okay, so the positive one is LFR, and then our negative ones are, these are L over 4 FM minus L over 2 times the weight. So now we have these two equations, this one and this one. And we want to know, the question asked us what the forces from the scales are. So that's the FL and FR. So let's take a look at our equations. 0 equals FL plus FR minus FM. Actually, Yeah, no, I'll leave it. I'll rewrite them in a second. And then our other one, 0 equals LFR minus L over 4 FM minus L over 2 times the weight. So it looks like when I look at this, one thing we can do, it looks like we could solve for FR and plug that in here, and then we can use that to solve for the force on the left side. Yeah, because again, FM is big mg and weight is little mg. So let's rearrange this equation. Actually, first we can divide L out of all of it because it equals 0 and every term has L in it. So we'll divide the length out. And then we have, and we'll add these guys to both sides. So what we end up with is FR equals 1/4, and I'll plug in what they really are. Big mg plus 1/2 little mg. And actually, I'm realizing now, we could just solve that really quick to get a number. So let's plug in numbers. Let's see, pick a different color. 1/4, the mass of the object, or of the mass, is 2.5 kilograms times 9.8 meters per second squared. And then we have plus 1/2, and the beam, the mass of 1.8 kilograms times 9.8 meters per second squared. So this is the force of R is 15.4 newtons. Now we can actually just plug that number in, or you can plug in these either way. Let's just plug the number in for this is faster. So plugging into this equation. Well, actually, before we do that, let's rearrange it so that we don't have to do that once our numbers are plugged in. So we will subtract FR from both sides and add these guys to both sides. And that leaves us with the force on the left is force M plus the weight minus force on the right. So this is big mg plus little mg minus FR. Now we can plug in our numbers. Again, this is 2.7 kilograms times 9.8 meters per second squared plus 1.8 kilograms times 9.8 meters per second squared minus 15.4 newtons. And this is 28.7 newtons. So there we have the force on the right and the left. The most important things I want you to take away from this problem is the extended free body diagram, super important. We haven't always been great about our free body diagrams, so please make sure you put some energy and focus into the extended free body diagram. And then using a table to keep track of your torques. I highly, highly recommend that because it makes it so much easier to deal with torque. Because really it's not that different than just forces. But again, there's a lot of things that you could lose track of. So I highly recommend a table. Okay, let's do another example. 1 second. Okay. Our participant in a strongman competition uses an old-fashioned device to move a large load with only muscle power. A 1-ton or 910 kilogram bucket of rocks is suspended from a sturdy lightweight beam 0.85 meters from the pivot. The man lifts the beam at its end 3.6 meters from the pivot and holds it steady. How much force must the man apply What is the force on the beam from the pivot? So first thing we do is draw our extended free body diagram. So draw the beam. And then the man is holding it up, so that's a force pushing up. We'll call that force man. And then the bucket of rocks, or yeah, that's what we call bucket of rocks. That is applying a weight, force down, and that force is just the weight of the bucket. And then we have the pivot, which is also applying an upward force of the pivot. And let's get our distances. So the pivot is our pivot point. So we have this distance, we'll call it our B for bucket, and it is 0.85 meters from the pivot. And then we have the distance to where the man is holding the beam, and that is RM, and that is 3.6 meters. Yep. Okay. We are going to also need the sum of forces. So let's just do that really quick. And then we'll move on to the torque. So I'll just do it here. Sum of forces in the y direction is 0, and that is the force of the man plus the force of the pivot minus the weight of the bucket. Okay, so we'll save that for later. We don't need it right away. But let's do our sum of torque. So I'm making my table force, distance, sine theta, and the sine of the torque. And let's see, I'm gonna pick a different color. There we go. We have, we'll start on the right side. So F pivot, 0, doesn't contribute torque. F man, I guess I didn't, and here, I'll start on the right side. We'll do the weight of the bucket. That's RB, or 0.85 meters. Sine 90 is 1, and we'll do the sine of it in a second. And then force of the man, distance is 3.6 meters, also sine 90, and let's do the sine of the torque. So holding at the pivot point, pulling down at where the weight is applied, and so that's counterclockwise. So the weight, positive torque, and then the man pulls up, and that's a negative torque because that's going to be going clockwise. Okay, so I don't have a ton of room, but I think I can write my torques here. We'll call this B torque, our tau beam. I'm just going to write the variables, not the numbers here. And the man, RM, force man. Okay, so the first thing it asks us for is the force the man applies. So let's get our net torque, which again is 0 because we're still in equilibrium situations. And so we have the torque from the bucket minus the torque of the man holding the beam. And that is RB, weight of the bucket, minus RM, force of the man. So, and this all equals 0, so we can, we know our distances, we know the weight of the bucket, so we can just solve for the force of the man, and we'll just add RM, FM to both sides. And then we'll also divide both sides by RM in a second. Dividing RM on both sides to get FM by itself. Okay. Now we'll plug in our numbers. So this is 0.85 meters. This is 3.6 meters. And then the weight of the bucket. Okay, so we were given the mass, 910 kilograms. And then we need to multiply by acceleration due to gravity, meters per second squared. So this force is 2,100 newtons. that is the force that the man applies. I'll highlight this. And then we're also asked for the force the beam applies, and we know because or I'm calling it the pivot, sorry. The force the pivot applies, and we know because it's the pivot point that it didn't apply any torque. But the reason, that's still the highlighter. The reason we did this on the force equation ahead of time was because that's where the pivot force is. And now we know the force by the man and we know the weight, so we can find the pivot force. Let's move it down here. So 0 equals the force by the man plus the force by the pivot minus the weight. And so we will just add the weight to both sides and subtract the force of the man from both sides. And that gives us the force of the pivot is the weight of the bucket minus the force of the man. So I'm going to plug in 910 kilograms times 9.8 meters per second squared minus 2100 newtons. And this is 6,818 newtons. We could probably round that, but I'll leave it for now. So that is the force provided by the pivot, which honestly is a lot more than the force provided by the man. But alas. Okay, so we're gonna do one more example, but this one we're no longer in equilibrium. There is acceleration happening. And so I want to show you how to combine both torque and other rotational motion things. So the problem is a pulley, which can be considered a uniform disc of mass 2.5 kilograms and radius 20 centimeters, mounted on a fixed frictionless horizontal axle. A block of mass 1.2 kilograms hangs from a light cord that is wrapped around the rim of the disc. Find the acceleration of the falling block, the tension in the cord, and the angular acceleration of the disc. So that's a lot of things. Right, what we want. We want acceleration, we want the tension, and we want the angular acceleration. And we're told that this is a disc rotating about its center, so we can just use the rotational inertia for a disc about its center, which you should look up in the table, but I already did. So it's 1/2 mr squared. Okay. And one other thing I'm going to write down is the relationship between the acceleration, which in this case is the tangential acceleration, and the angular acceleration, which is just tangential acceleration equals angular acceleration times r. Okay. Now let's draw our a free body diagram for the mass and then an extended free body diagram for the pulley. So here's the one for the mass. It's just its weight, the tension, and I didn't draw these exactly to scale because it's accelerating down. The lovely picture I drew, and also the picture in the slides for this one indicates the direction of the acceleration, which is down. Now we'll do the extended free body diagram of the pulley, which has a radius r. And so there is its weight force, weight pulley, but that's acting from the pivot point, so it's not going to contribute to the torque. But then we have the tension also. Okay, so now for the net torque. Think for a second. Maybe actually I'll do the net force first. So sum of forces on the mass is its mass times negative acceleration because it's going down. And then that equals the tension minus the weight. Okay. Now I'm still gonna do the table just because I want you to be doing it for torque, but there's actually only one torque on the system. So, oh, let's make that sign theta, and then the sign is in direction. So the first force we'll say is the weight, and that's at the pivot point, so it doesn't affect anything. And then we have the tension, which acts at a distance r, the radius, and that is sine 90 is 1. And then let's look at the direction. Actually, you can just kind of look at that and see, but it's a good practice to have pivot points in the middle, pulling over on the side. That's going to cause counterclockwise rotation, so that's positive force. So now let's do the sum of torque. Sum of torque equals I alpha, which also equals the torque from the tension, which is just R times the tension. So here's our equation. And just looking at them face value, we have 3 unknowns. That's not solvable. But technically we have 3 equations actually, because we have this relationship between angular and translational, or tangential really, acceleration. So we just do the algebra of it. Let's write our equations over here. I'm going to leave out the sum of part. Oh, actually, and I'm going to plug in for the rotational inertia. 1/2 r squared equals RT, and that's, we can divide r from both sides and just simplify things slightly. So 1/2 mr equals the tension. Cool. And the other one, we have negative MA equals tension minus mg. So right here, we could just, we can just plug this in for the tension. I forgot the alpha though. That's bad. Alpha, there we go. And we should probably sub in what alpha is, which is the acceleration divided by r. So we'll just plug that in here. We have negative MA still, and then we're plugging in for the tension, which is 1/2 mr, and then we're going to plug in for alpha A over r minus mg. Sorry, these are not all the same mass. 1 second, let me figure out. This one is the mass of the pulley, so I'm just going to make that capital M. Because when I was practicing this is where I messed up and got the wrong answer, because I pretended they were all the same math. They're not. Okay, there we go. Let's do a little canceling. These r's go away, and then we will, because I like to eliminate negative signs when I can, add mg to both sides and also add ma to both sides. So we end up with mg equals 1/2 capital MA plus little ma. And we can factor the a out. So we end up with 1/2 m plus little m times a. And then we can divide the parentheses from both sides to get the acceleration by itself. So we get mg 1/2 m plus m equals a. And we can plug stuff in. I don't remember any of the masses. Actually, I have it up here. Somewhere. Let's see. I'll just check here. Okay, so the weight that's hanging down is 1.2 kilograms. It's 9.8 meters per second squared. And then the other mass is 2.5 kilograms and plus 1.2 kilograms. And so this gives us an acceleration of 4.8 meters per second squared. So that is the acceleration. Let's get the angular acceleration. Angular acceleration is the acceleration divided by r. So 4.8 meters per second squared, and r is 20 centimeters, so 0.2 meters. And this gives us an angular acceleration of 24 radians per second squared. You could also convert that into radian or into revolutions. But we're not, because we don't need to. And finally, the tension. Let's see. Oh yeah, we'll just use this equation here. So the tension equals 1/2 mass of the pulley, radius of the pulley, angular acceleration. Yeah. So 1/2, 2.5 kilograms, 0.2 meters, and 24 radians per second squared. Almost ran out of room. And that is 6 newtons. For the tension. Okay, so that the important thing from this problem, and also the thing I didn't actually explicitly talk about is the side of the pulley has that tangential acceleration, but because we're like rotating without slipping and there's not friction, the rope itself and therefore the hanging mass all have that same acceleration. That was part I didn't actually specify. Yeah, so this is how we deal with kind of use Newton's second law with force and torque. We found we drew free body diagrams and the extended free body diagram. We did our sum of forces, and we also did our torque table just because, and sum of torque. And then we had our two equations, and well, technically 3 equations and 3 unknowns. And then we just did our algebra. So again, it's not, I swear it is not that different from what we've been doing with force. I know it's easy to get kind of freaked out because it's rotating and there's some like less familiar looking variables and we're using Greek letters. But I swear it is not that different. And as long as you are careful and keeping track of the forces acting and therefore the torque they're supplying, it'll be okay. And you will be working on this in your assignments for this lecture.